Welcome to Maths with EJD. We're still talking about spectral analysis, and in this video, we're talking about time frequency analysis. Already, the whole idea of spectral analysis is connected to Fourier theory, where a function, a signal, or a data set in the time domain is transformed into the frequency domain where we can actually see the frequencies. We can look at these signals or data sets in terms of frequencies instead of just what we see in the time domain. So here, let's talk about time frequency analysis. Okay, so time frequency analysis actually studies signals whose frequency content changes over time. So if the frequencies change over time, then we can do time frequency analysis on that. So unlike Fourier analysis, which assumes stationarity, so you do Fourier analysis when you have stationary frequencies. Time frequency methods allow simultaneous examination of both time and frequency, so which is crucial for non-stationary signals such as speech, music, biomedical signals, or vibrations, right? So so when you talk about key concepts for time frequency analysis, you have non-stationarity signals. So here you have signals with changing frequency content over time, and then you have time frequency representation, which is joint representation showing how signal energy evolves in both time and frequency. Then you have applications in speech processing, biomedical signal analysis like for EEG, ECG. Then you have for mechanical fault detection and radar vibration, radar and communication. Of course, for mechanical fault detection, this can be given away by things like vibrations of machines. So there's a way a car is vibrating, and then you can know there's something wrong with it. So let's talk about short-time Fourier transform, STFT. So the short-time Fourier transform analyzes small portions of a signal using a sliding window, assuming local stationarity within each window. So if we assume a local stationarity within each window, we can look at just that window, and that is why we have short-time Fourier transform, STFT, where x of t is the input signal as usual, and then we have W of t, which is the window function, whether it's Hamming, Han, or Gaussian. Then we have the time shift parameter. So that's t right there. And then you have the omega, which is the angular frequency, like that. So the magnitude x of t comma omega represent the spectral content at time t. So the spectral content at time t, that's the x for you. That's what you see right here. So the short-term Fourier transform of x of t, the short-term Fourier transform of x of t for t comma omega is big X into of t comma omega, and that gives you this whole integral from negative infinity to infinity of x of tau, w, that's the window now, window of tau minus t e raised to minus j omega tau d tau, like that. So let's look at windowing effects. So for window type, the rectangular window type, that's when the window function is just one. So the characteristics of this window type is that it has a sharp cut and it has poor spectral leakage, and it's the typical use is very rare. It's hardly used because nothing is actually changing, right? Then you have the hand stroke Hamming. They look really close in this case. So the characteristics, they are both smooth and you have reduced leakage, and they are the most common of all. Then you have Gaussian, which is smooth and best for multi-resolution analysis. It is advanced, in use. So for trade-off now, we can talk about the Heisenberg uncertainty principle. I think that came up when we're talking in physics, when we talk about light, the wave particle duality of light and all that. So if you have a narrow window, that will give you high time resolution and but poor frequency resolution. But if for a wide window, you have high frequency resolution and poor time resolution. Okay, so if you want high time resolution, you go for narrow window. If you want high frequency resolution, you go for a wide window. Okay, so let's talk about the spectrogram. A spectrogram, actually, spectrogram is the magnitude squared. It is the square of the magnitude of the short-term Fourier transform, and it is visualized as a time frequency map as we're going to see very soon. So the spectrogram of T, F, the spectrogram given a particular time and frequency is equal to the absolute value of the square of the absolute value of x of T, F. So it shows how signal power is distributed in time and frequency, how signal power is distributed in time and frequency, and how do you draw a spectrogram? That's what the next, this Python code is about. So of course, here we need NumPy, Matplotlib as usual for numerical computation and data visualization as usual. And then we need to get spectrogram, we need the scipy.signal module. So from there we get the spectrogram. So we have a sample signal, which is sum of two sinusoids, which one is transient. So you have Fs is 1000 for that's the sampling frequency, and then you have T is np.linspace 0,1 Fs, and then you have it's sum of two parts as usual. So you have a frequency of 50 and then another one of 120, and then here we have time less than 0.5 and all of that. So then you can compute the spectrogram because you have a function for that. So you don't need elaborate coding for it. You just need to call the spectrogram function. So you have the function T_spec, you have SXX. These are the values it is going to spew out for you, I believe. Then you have spectrogram, and the input it will take is the signal or data set, the sampling frequency Fs, and the number n per seg, which is 120. I believe that should be a number of samples per segment. Since we're talking about short windows like that. So then to plot this now, you need, instead of regular plot, you need a P color mesh. You need a color mesh here. So it takes the T-spec you get from the spectrogram. It takes the function also, and then that goes by 10 log 10 of the SXX that you also get from the spectrogram, and the shading is Gouraud, or you can change the shading to other ways. So you have the Y label, that's frequency, X label is time in seconds. We are talking about a spectrogram, and the color bar talks about the decibels, it's about like sound. So if I run this now, it takes a bit of time when you run for the first time in Google Colab. So now we have it done. So we have this beautiful figure out here. So if you're looking for regions of high decibel, you have them up here, around this place up here. And then all these bright sides, you have lower, the power is not as strong in all this. Oh, these are negative values, actually. These are negative values. So yeah, I mean, the same, yeah, for negative values now. So it means areas of strength are all these negative ones, while areas of weakness are all these darker sides. So the brighter, the stronger. That's the idea here. They're talking about the time frequency combination that spectrogram represents. So let's go ahead. So for time frequency analysis, right? I think there are two key things. You have the SFTF, that's the short time frequency Fourier transform, and then another one is a wavelet transform. Okay, there are all kinds of wavelets. So wavelet transform overcomes STFT's fixed resolution problem using scales instead of a fixed window, enabling multi-resolution analysis, right? Now, the beauty of this, we couldn't get this in Fourier because we had fixed stuff, but here you can look at different times and different frequencies since they are both changing in this case. That's why time frequency analysis is really important. So wavelet transform overcomes STFT's fixed resolution problem using scales instead of a fixed window, enabling multi-resolution analysis. So for high frequency, you get good time resolution, and for low frequency, you get good frequency resolution. So it's all about the frequency. So wavelets are localized in both time and frequency, making them ideal for transient signals, right? So a very good example of that would be a continuous wavelet transform, like that, CWT, continuous wavelet transform. So for a signal x of t and a mother wavelet psi of t, so the continuous wavelet transform of x of t for parameters a and b is equal to xab, which is 1 over square root of the absolute value of ab, integral from minus infinity to infinity of x of t, then the complex conjugate of the mother wavelet into t minus b over a the T, right? Where A is the scale, which is the inverse to frequency, and B is translation, talking about time shift. Then you have psi of T, which is mother wavelet, and you have the star, of course, tells us that. So psi of star is the complex conjugate of the mother wavelet. Okay. Then we have the common wavelet families. So there are different, like I said the other time, there are different types of wavelet families. You have the Morley, which is the use case for that is for time frequency analysis and for oscillatory signals. Then you have the Mexican hat, which is good for feature detection and transient events. You have the Dope cheese, which is good for compression and multi-resolution analysis. And you have the Haar wavelet. So Morley wavelet, Mexican hat wavelet, Dope cheese wavelet, right? And then you have the Haar wavelet, which is good, simple step-like signals for DWT basics. Well, DWT is what's DWT again? I'm trying to remember that. Something wavelet transform. Yeah, continuous wavelet transform is CWT. Okay, so this for DWT basics. Okay, let's look at the Python code. So in this case, we import PYT, right? So here, continue. So we have a library called PYT, and that's what we use for continuous wavelet transform. So we talk about the scales np.a range from 1 to 128, and then you have so whatever you get is going to give you coefficients and frequencies. So you have pywt.cwtx, you have the scales, you have the mol, then the sampling period is 1 over fs, then you show the imaginary side, you have the extent 0, 1, 1, 128, CMAP is jet, aspect is auto, and you have all of these things. So if you run that, you can see the continuous wavelet transform. Another beautiful contour plot if like that. So here it talks about time and scale in this case. So, and this overcomes the limitations of SFTF or so. Um, STFT, yeah, STFT, short-term Fourier transform. So this is the continuous wavelet transform. So, and here we talk about the magnitude. So the reddest side is where you have the highest magnitude, and the bluest side is where you have the lowest. So you have somewhere around maybe 200 and 120 scale. You have so some redness right there, and you have some light all over the place like that. So then of DWT is discrete wavelet transform, yeah. So discrete wavelet transform provides efficient, non-redundant representation using filters. So it is used for signal compression and denoising. Okay, so I mean it's removing noise, right? Wavelet coefficients are split into approximation like low pass and detail, high pass components. So we have approximation and detail components. So approximation is low pass, while detail is high pass. And then we have a Python code for that. We still use the PYWT function like before. Okay, so this is the discrete forward and inverse wavelet transform, stationary wavelet transform, wavelet packet signal, decomposition and reconstruction module. So we have DWT decomposition. So here we have the sampling frequency. I mean the usual things. Usually need the sampling frequency, you need the time range, and you need the signal itself. And we always use the 5120 frequency signals. Then we perform discrete wavelet transform up to level 4 using dope cheese 4 wavelets. And then, of course, we get the coefficients by applying by getting the wave deck from the PYWT library. And then, so we supply it with X. Then we have DB for level 4. So you have CA4, CD4, CD3, CD2, CD1, and you have the coefficients. So this is approximation and detail coefficients. Then you can plot original signal and wavelet coefficients. So at this 0, you have plot T against X. So at the 0 set title, you have the original signal, you plot that. Then if you plot CA4, so which are the coefficients, right? So for CA4, you have approximation coefficients up to level 4. Then you have CD4 detail coefficients level 4, CD3 detail coefficients level 3, CD2 detail coefficient level 2, CD2 that is CD1 detail coefficient level 1. That's what all of these things actually represent. So if you run this now, you can see all the discrete wavelet transform, the composition. So like this. So it bears a bit of resemblance with when we do the data decomposition, where we have residuals and things like that. So you have the original signal like this, all right? So you see the frequency changes after some period. Then you have the approximation coefficients at level 4, it goes this way. Detail coefficients, you have this. Then you have detail coefficients at level 3. it's more together. Then you have detail coefficient in level 2. So it's looking like a damping kind of situation. So same for level 1, like that. Then we can talk about the energy distribution per level. So, in the case of time frequency analysis, right? So part of the things we are looking at here is energy distribution per level. So here we define the energies. You have sum of C squared, right? For C in coefficient. So you pick your coefficients, you sum them up, and then total energy, that's sum of energies also. So you're summing up these energies you're getting from here. So for C in whatever, we had coefficients up here already, right? So yeah, of these coefficients up there. So you pick them, all the CD4 and all the rest of them. So then you sum up the energies. The energy percent is now 100 times E over total energy for E in energies. Then you display energy distribution. For I and E in enumerate energy percent. So you do level approximation A for if I is equal to 0, else detail 5 minus I and all that. So you can study that and tweak that and you get different levels. So approximation A4, you have 10.71% of total energy, detail D4, 48.39% of total energy, detail D3, 27.15% of total energy, detail D2, 13.49% of total energy, and detail D1, 0.25% of total energy. So as it's going up, the energy seems to increase. So let's talk about signal reconstruction, both full and partial. So here we want to do full reconstruction, original signal from all coefficients. So you have partial reconstruction, keep only approximation A4 to remove high frequency details. So you have coefs underscore approx only. So you have CA4 plus none by 4. So you keep A4, discard all these in this situation now. So all these are gone. So X approx, you get waverect from PYW for coefficient approximate only, and then DB4. Then that's for partial reconstruction. So for partial reconstruction, you still keep approximation and lowest detail D4 now. So you have CA4 and CD4. Here it was only CA4. So here it's now CA4 and CD4 and none by 3. So X low pass, waverect again, and you pick that in. And then you go ahead and do your plotting. Plot original versus reconstructed signals. You have TX label original signal alpha 0.8, X reconstructed. You can study this to understand better what this is all about. So I just run this and we get the signal reconstruction, both full and partial. So look at this now. We have all the signals. The original signal is blue. So you can see it, somewhere in the background. And then for the full reconstruction now, you have the orange color. For approximation only, which is for A4, you see this green line going there, and then A4 plus D4, that's the red one. So that one is it has higher amplitudes like that. So that's for signal reconstruction for wavelet coefficient. Then we can also do noise removal, right? That's wavelet denoising. So how does that work? So you want to add white Gaussian noise to the signal, for instance. So you can have random seed because we want to add random noise, right? We do random seed to make sure that it is reproducible each time. Because if the line 2 is not there, so each time you run the code, you're going to get another value entirely for the noise. So that's why the random seed, the seeding is important. So you have 0.3 times random length X, right? So that's the noise. So this is the noise now that we're adding to. So X noise, now you have the actual signal X plus the noise. That's the X we have defined before we got here, before now. So you decompose noisy signal. So you have coefficients, noisy, wave deck. I think there's need to show this X again. So it's the X, the last X we ever declared. That's what we've been using all the way. Yes. So this same X is what we are using in other cells so that they are connected together. Okay, so here now we have so we want to try to denoise, right? So we add noise so we can then remove the noise. So X noisy is X plus noise. So we have coefficient noisy. So you have X noisy DB for level 4. Apply thresholding to detail coefficients. Okay, so you have soft threshold like that. So if you can have a threshold of 0.6, so it means you can vary this. You can change it to whatever you like. So you can have coefficient denoise. That's coefficient noise is 0 plus PYT dot threshold C threshold mode soft for seeing all the coefficients of noise from 1 to the end. All right, so you can then reconstruct the noise signal. So X denoise now is PYT waverect coefficient. So this is the reconstruction. Then you do the plotting here like we've been doing. So I run this now, and then so you have the original signal now. That's with the noise, I think. Okay, the original signal is blue, right? Then you have the noisy signal when you have added the noise. So you see, it goes up a bit, but it has higher amplitude. As you can see, the orange is shooting up better. But then the noise signal is when you now put it back to normal. And then it's even better than the original because probably the original already had some noise before. So you then added noise to it, and then now the noise. So you have the amplitude not up to what you had for even the original, which is in blue. So here we can then talk about comparison, right, of STFT versus wavelet transform. So we see what for time frequency analysis, we use STFT, that's short-term Fourier transform or wavelet transform. So here now, talking about time frequency resolution, STFT is fixed while wavelet transform is scale dependent and it's good for multi-resolution. So STFT is best for stationary signals, while wavelet transform is best for transient and sharp events. STFT, the complexity is low. Wavelet transform moderate. The complexity is moderate to high. STFT. To visualize STFT, use spectrogram, and to visualize wavelets, use scalogram, right? And to adaptivity of STFT, no adaptivity. But for wavelet transform, it is adaptive to frequency. So what are some applications of frequency time analysis? So speech and audio processing. So for like formal tracking, pitch estimation, biomedical signals like EEG, ECG analysis, seizure detection, mechanical systems for diagnosis in rotating machinery, talking about vibrations, right? In communication systems for modulation analysis, interference detection, finance and geophysics, pattern detection in non-stationary signals, right? So some practical tips. STFT window selection, choose based on fastest changing frequency. Zero padding improves FFT resolution, not actual frequency content. Zero padding helps us to extrapolate, and then we can get more points. So it makes things smoother. Wavelet selection, MOLET for oscillatory signals, DOPCHIS for transient. So if you're dealing with oscillatory signals, you want to use MOLE, MOLE wavelets. Normalization, you can scale wavelet coefficients for quantitative comparison. And visualization, you can use log or dB scale for power representation. And with this, we come to the very end of this interesting video on time frequency analysis, so it helps to do what Fourier transform cannot do, because Fourier transform only takes care of stationary values. But when we have non-stationarity, we go for time frequency analysis using either short-term Fourier transform or wavelet transform. So with this, I come to the end of this video. Let me know how helpful this video is for you. If there's something you like want to try, feel free to let me know. You can also, of course, if you have subscribed already, thank you so much. If you haven't, this is your time to subscribe. Please go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. You can also take it higher. You can become a member of the channel. Just click on join. You see some nice perks, nice privileges awaiting you as a member of the channel. Ultimately, don't forget to like, share, comment so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.